To solve using the row operations, and we've seen a example where z can be anything, but x and y is determined based on the z value. So we can further introduce the general solution. I'm going to change the order of the book for a little bit. So first we start with the definition. If we have a linear system, ax equals 0, where x and zeros are vectors, is called homogeneous. And for any system ax equals b, a system is associated with a homogeneous system. Okay, so using the example we've seen yesterday, so we have the three equations, y equals to 1 minus 2z equals 3, x plus y minus 3z equals 7, and x plus 3y minus 7z equals 13. So we've ended up with this equation. And then the associated homogeneous system is when you just change the right side to be zeros. So same equations. And just change the right side to be 0. Okay, so our steps will be the same. And since we are just doing like row exchange, one row minus the other row, and some multiplication with the plus or minus, then basically, since our right side are all zeros, our right side would not change, but only the left side, we would be left with the original left side. So we would end up with 0, 1, 2, and 0, 0, 0, with the right side to be all zeros. And this is similar to write in x, y, and z, where z is just z. Here on the first one, x minus z is 0. So that means x equals z. And then the second line is y plus 2z is 0. So y equals negative 2z. Okay, now to write using the vector. Here x, y, and z can be written as z multiplied by 1, -2, 1. So these two are very similar. No, these two are exactly the same. And 430 is just a specific value that we solve for this equation when b equals 3, 7, 13. So then, since we know the solution for ax equals 0, and for any solution, okay, let's name this. So this 4, 3, and 0 is a particular solution to ax plus b.
Ax plus b.
To ax plus b. A particular. I mean, ax equals b, my bad. Because changing the b, we basically change this 430. And then this on the right side, we call it the full solution to a homogeneous system.
So
And again, homogeneous system is just ax equals 0.
wait, can you zoom out for a second? Like zoom out. Okay.
Cool. So this general solution, we can write it as so the general solution our solution x would be equal to the particular solution xp plus the homogeneous solution x sub h. And then So after having this general solution, basically we can last class we've introduced the kernel. We can use this general solution to find some kernels of this transformation. So as we know this matrix A, so our augmented matrix, we always write it as a matrix A on the left and the vector B on the right. So we know that this matrix is associated with a linear transformation T.
Mhm.
And for this T, we can actually find the kernel of T with this general solution. So in this case, our matrix A is uh, is the matrix on the right, on the left. So 0, 1, 2, 0, 1, -2, 1, 1, -3, 1, 3, -7. And we say this general solution, this vector multiplied to z is actually a basis to the kernel. So that means any linear combination of this 1, -2, 1 is like after the mapping, it will give us 0 as a solution.
Oh, because it's like proportional.
Hmm?
Because it's like proportional. Because it's all in terms of
Right. Right. So we say this is the basis for of kernel A.
I'm a bit confused about like the whole
Mm,
kernel thing. Like,
kernel is the subspace where and everything maps to 0
oh,
after
okay.
the transformation.
But if the matrix represents the transformation,
Mm-hmm.
then the kernel, because if the matrix represents the transformation itself,
Mm.
then like how do you go from that to getting the kernel, given that the transformation, like do you have to actually like multiply the matrix by like a vector?
Yes, we can actually. So this is so finding the general solution to a homogeneous system is the way to find the basis of the kernel. And after finding the basis, we can just do linear combination to find the vectors. So that's why we introduce the homogeneous system. So we just need to set this transformation A multiplied by some vector, some unknown vector equals 0, and then we will get the basis. So
Oh,
one example in this case, one element in the kernel could be the basis of itself, or it's just one multiplied by the basis. So for example, if I multiply this A by this kernel, let's call it K1. Then after we do the multiplication, since matrix multiplication represents the transformation, we will end up with 1 multiplied by 0, 1, 1, minus 2 multiplied by 1, 1, 3, plus 1 multiplied by -2, -3, -7. Mm.
Isn't it isn't it row times column?
Yeah, it is, but it also equals this. Wait, what did I do wrong? Mhm. Because what I have here should be equal to what I have here. Mm, oh no, wait. Uh, so hmm, not equal. Would be minus 2. Oh, wait. There was there was some mistake when I do the computation. I
Mm.
was so here was -2. I copied it wrong. So so right here should be y minus 2z. And here y equals 3 plus 2z. So z is 1, 2, 1. Z multiply 1, 2, 1.
Not neg.
Okay. So here as well. So here should be -2. So here will be a positive 2z. And here is a positive as well.
Oh,
Right, my bad. I was doing some wrong copying.
and then before that step. Oh,
Where?
oh, never mind.
Cool. Okay. Some mistake from last class. All right, so then when we do the multiplication, we'll get the correct answer. So I'll have the first line is just 0 plus 2 minus 2. Second line is 1 plus 2 minus 3. Third line is 1 plus 6 minus 7. And this gives us the 0 vector. All right, so this is one example where using this transformation, after this transformation, we multiplied by something in the kernel, but not the zero vector itself. But after the transformation, we also get the zero vector.
Mm-hmm.
Uh, now, so this is a way to compute the kernel. And we can have another example with more lines. So if we have each matrix A, it equals 1, 2, 3, 1, 2, 3, 1, 1, 2, 3, 1, 2, 5, 7, 3. 1, 3, negative 1, 1, 1, 2, 0. Okay, now we have this matrix A and we want to find the kernel of A.
Mm-hmm.
So we now know that first we can solve AX equals 0, solve the homogeneous system. All right, so basically we still follow the row operations and do the reduced row echelon form. So this will be, I'll just tell you the answer after the reduced row echelon form. We will get a matrix again with 4 rows and 5 columns, with first row to be 1, 1, 0, 8, 3. Second 0, 0, 1, negative 3, negative 1. Then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Right. And on the right is the 0 vector.
Mm-hmm.
Okay, so this matrix basically tells us, so if we call this x1, x2, x3, x4, x5, we have 5 unknowns. Then we know that x1 plus x2 plus 8x4 plus 3x5 equals 0. And x3 minus 3x4 minus x5 equals 0. So here we know that basically, although we have four equations, because each row represents an equation, although we have 4 equations, we only will be end up with like 2 actual equations after the reducing or row
Mm-hmm.
reducing. So 5 variables with 2 equations, that means we will have three variables. So we know that we can represent x1 equals something, but we have no knowledge on x2, and then we can also represent x3 equals something, but then x4 and x5, we don't know anything about them. So basically, if we want to write it as x1 equals something, we will have so from the first line, we can write x1 equals negative x2 minus 8x4 minus 3x5. And then from the second line, we can write x3 equals, okay, equals 3x4 plus x5. Okay, now we are left with x2. It'll be x2, x4 equals x4. And x5 equals x5. So those three are free. Okay, now we can further rewrite this new system of equation to be x1, x2, x3, x4, x5. So our x right here, x factor equals x1 to x5, and it will be written as so we're going to represent x2 as x2 multiplied by a vector, which is the first one. X1 has a negative x2. So then we are basically representing x1 with x2. So that's a negative x2. And x2 is just 1 multiplied by x2. Wait, this is negative. Okay, x3, but we do not need x2 to represent x3. So this will be a 0. And similarly for x4 and x5, we do not use x2 to represent them. Okay, similarly, this will be plus a x4 multiplied by, okay, x1 we need to multiply a negative 8 on x4. x2 we do not need x4, x3 we need a 3, x4 we need 1, and x5 we need nothing. Okay, similarly for x5. All right, that one we need to multiply by a negative 3. And then for x2, nothing. x3, a1, x4, nothing, x5, a1. So again, these 3 vectors, we can call it k1, k2, and k3. And these are a basis of the kernel A. So it means that any linear combination of these 3 vectors would result in a after multiplication with A, we would get to the zeroth vector, the zero vector.
Mm-hmm.
Wait, so there was one theorem. So basically, if we introduce first f to be the number of free columns in A prime, and this A prime means the matrix A, but in the reduced row echelon form. So if we know this is A, then this form is the A prime. Mm. And then we introduce P to be the number of pivot columns in A. A prime. So these two means number of pivot column is when we see a pivot, and again pivot is when
Like a leading.
yes, when the leading entry is 1 and everything above this entry is 0. So these two are the pivot column. And so the free column is just where we have else, these three. Free columns. And we haven't introduced the dimension of a vector space yet. But basically we say the dimension of a vector space is the number of bases that can be formed, that can be used to form this vector space. So in this case, since the number of free columns in for A prime is 3, we say the dimension of kernel A is 3. So F would be equal to dimension of kernel of A equals F. So this is actually a theorem saying the vectors k1 through kf corresponding to the free variable is a to be a solution to ax equals 0 are a basis of kernel A. And again, to prove basis, we're going to prove the span and linear independence. I'll skip this for now, but this is this is also closely related to the range or the image of A. So the dimension of the image of A actually equals the number of pivot columns. And the basis of the image of A is, let me find values the red is so these two pivot columns are corresponding to the first and third column. So these two are the basis of the image A. Oops. So this. Okay, we can also do the proof for this, just like the proof for the kernels, the basis of the kernels. But to do that, we are going to introduce some of other theorems. Okay. So let's pulse from the kernel image and start to analyze the pivots. Mm. So first we define the linear system AX equals B is called consistent if it has a solution.
Mhm.
So as long as it has one solution, we call it consistent, and we call it inconsistent otherwise. So one example of a inconsistent system is when I have x plus y equals 0, and I have x plus y equals -1. So we cannot solve for solve for x or y with these two equations.
Oh, yeah.
Mm,
So basically, like no solution.
right. So then we call it inconsistent. Um, and this equation can be written as 1, 1, 0, 1, 1, negative 1. And we can actually reduce it to 1, 1, 0, 0, 0, 1. So basically used row 2 minus row 1. Okay, so in this case, our pivot wait. And then we can multiply by -1 on the right, on the second row to get 1. Let's do that. Or so keep the first row 1, 1, 0. And the second row, we can use R1 minus R2 to get 0, 0, 1. So the pivots for this augmented matrix is here and here. So then we can conclude that as long as the augmented matrix row reduced to having a pivot in the augmented column, then AX plus B is inconsistent.
Um, so even if it's like, oh, you mean yeah, okay.
Mm,
But if it was like +1, I mean, sorry, if it was -1 in the equals column.
then we just multiply by -1.
Oh, okay.
Yeah. Row reduced to if and only if AX plus B AX equals B is inconsistent. Right. And now let's introduce some propositions. Okay, before this proposition, let's again define out of the A prime to be the reduced row echelon form of A.
Mhm.
Mm, station. Okay, propositions. First, ax equals b has at most one solution,
Mhm.
meaning that either it has one solution or it's inconsistent. If and only if a prime has a pivot every column.
Is it because then you have like I don't know if this is the correct way to explain it, but like then every variable is like tied to something?
Mm,
Like
then what do you mean by tied to something?
if you have a pivot in every column,
Mm,
then that means not one variable is just a zero vector, right? It isn't just like 0, 0, 0, 0, 0. So that means it's like it's always like defined, like it's always present in some equation. Well,
right,
yeah, I don't know how to explain it.
right. So basically, for every column means every column in our case represent a variable. So every column means there's no free variable.
Yeah.
Yeah. So if there's no free variable, then either we can cover all the variable and solve for all of the variable, or we're too restricted to have no solution.
Oh, I see.
Mm. So second, ax equals b is consistent, means that there's more than one greater or equal to one solution. If and only if a prime has a pivot in every row. But then for this example, as long as there's no pivots in the augmented column, then we have pivots for every row in this sense. Because we basically like don't need to consider these tools. We can only write like these um these two equations.
Mm-hmm.
So then we say a pivot in every row means there is no pivot in the augmented column. So then ax equals b is consistent.
So like for instance, if you look at the example above, if it was like 1, 1, 0 and then 0, 1, 1,
Mm.
then that would just be y equals 1.
1, 1, 0 and 0, 1, 1, you said?
Mm-hmm. Because
So
then you
if
have a pivot in every column.
if here is one,
I mean, you have a pivot in every row. Sorry.
yeah, yeah. if I have a 1 here, then I will be able to solve this equation.
Okay.
Okay, so then the third one is we say ax equals b has a unique solution. If and only if it has a pivot in every row and column.